Okay, questions?
There's also a problem where we have to draw two chair models given us cyclohexane.
Two chair.
Two separate chair models.
Do you have an example?
It's example 2, cis 1,2 dibromocyclohexane.
So you have to draw the structure of that. Oh, you want to name something.
Well, if we're given a name and a structure, we would have to draw two chair conformations.
Oh, okay.
Four chairs?
It is if I don't, if what she's talking about is if I said write the two chair conformations of cis 1 terse butyl 3 methyl cyclohexane. So if I said draw the two chair conformations of the cis and then tell me which one is more stable, for instance. So the first thing you would need to do then is you would need to draw out the chairs, which most likely would be, this would be provided. So in other words, I would give you a chair, but you have to figure out where the axial and the equatorial bonds go. So if you said 1 terse butyl, typically what I do is I use the upper right-hand corner as my number 1. I mean, you could choose any carbon as number 1. That's just how you'll see it in the homework problems and in any of lecture notes. So that's what I would call carbon number 1. And then you could go carbon number 3, so 1, 2, and 3, or you could go 1, 2, and 3. It doesn't really matter to me which 3 you use as long as it's 3, as long as it's 2 carbons away. So in this case, and the other thing with these rings is that when you write the ring like this, they bold all of this. You'll see in the book they bold it. What they mean by that is carbons 2, 3. If you're looking at the ring kind of flat, carbon 2 and 3 is actually in front, and then the other 3, 2 is behind. So if you take your cyclohexane ring and you look at it on edge, this is always the front edge. That's why it's bolded in the book. So either way, I usually use this one. So I'd have to come in and say, okay, axial, equatorial, and then say axial and equatorial. So I would have to know that that's where the axial and the equatorial positions go. Okay. And even then, this carbon 3 could be carbon 1, as long as you put a terse butyl group and a methyl group on those 2 carbons. Which means that for these problems, you need to know what your terse butyl, sec butyl, terse penyl, sec penyl. There is no sec penyl, so you'd have to know that. And then what isopropyl, isobutyl, what those groups are, because I'll give you the name and you have to put the group in. And if you don't put the right group in, you may get half credit, you may not, depending on how much that changes the problem. So in this case, we know that the terse butyl group, so there would be the terse butyl group. We know the terse butyl group has to be axial and equatorial, because that's what happens in a ring flip. And so the only question that's left is, on carbon 3 for the left-hand structure here, where does the methyl go to make that molecule cis? Okay, take a minute. Where should I put the methyl group? Do I put it axial or do I put it equatorial? to make it cis. Okay, everybody got an answer? All right, so say it on 3, 1, and it's either axial or equatorial. 1, 2. Okay, I heard a couple equatorials in there. Is it so? I just want to make sure we're all clear on this because this is a point of confusion sometimes. Axial and equatorial don't have anything to do with cis or trans. They do, but they're not the most important thing. What dictates cis or trans is, are both groups above the plane of the ring? Are both groups below the plane of the ring? And if it's trans, one above, one below. Now, depending on the substitution pattern around the ring, it may be that they're both axial, or they're both equatorial, or one of each. As you go from 1, 2 to 1, 3 to 1, 4, it changes. So my usual comment is, well, you can memorize all that, but that's a lot of things to memorize. Or we can just approach it this way. Is this T-butyl group, is that T-butyl group above or below the plane of the ring? Above. Okay. How do I know that? Because it's on an axial position. So where should the methyl group go to be cis? It's got to go axial. So that methyl group has to be axial in order to be cis. Okay. Now, let me just come down here and say, what if it was 1, 2? Here's my tertiary butyl group. There's my hydrogen. Where would the methyl group in the 1, 2, if this was a 1, 2 problem, where would the methyl group have to go in order for this to be cis? Hold on to your answer for a minute. Okay. Where does the methyl group go down here? Does it go equatorial or does it go axial? Have an answer? Okay. 1, 2. It has to go equatorial. Okay. And so here the T-butyl group is clearly above the plane of the ring. Down here, I don't know. Well, what's this hydrogen right here? Above or below? Definitely below. That's going to make this position definitely above, since each carbon has to have one below, one above. So my suggestion is that whenever you may be a little bit confused, most people can determine axial and equatorial directions with minimal effort. It's the equatorials that sometimes cause you problems. And so if you can get the axials up and down in the right orientation, then it tells you where the equatorials go. So in this case, above, that methyl group has to be above. So it's different, 1, 2 versus 1, 3. And so that's my point, is as we go 1, 2, 1, 3, 1, 4, you have different combinations of cis and trans. You can memorize those or try and learn them, or you can just try and recognize which positions are above, which positions are below. And then you don't have to memorize any of that. Okay. Right. Everybody kind of with me here? So then over here, my carbon 1 and my carbon 3 to be cis. Over here, where does the methyl group have to go? On there, axial or equatorial? Everybody got an answer? Okay, 1, 2. So it has to go equatorial. And if you're not playing along saying something, hopefully you're saying something up here so that you can figure out whether you were right or wrong.
So does the cis and trans only work when there's like 2 groups, or what if there's like 4?
So if there's more than two groups, what's cis? Well, cis is like Gaussian anti for conformations. Cis and trans are like Gaussian anti. They only refer to two non-hydrogen groups. The minute that I put a third, let's say I put a methyl group here. Now, if I put a methyl group there, I'm allowed to compare two groups and tell you whether they're cis or trans, but I'm not allowed to look at that molecule and say, oh, well, that's clearly cis. And you'd be like, wait, what two groups are you talking about? So when cis becomes a name, it has to be unambiguous exactly what it is. With three groups on there, that is not unambiguous. Now, how would I tell you in the name? I need to use RNS, which is a week or so away. So I can't do that with cis or trans. Cis and trans is only when you have two groups. Now, it's perfectly legal for me to say that this T-butyl group and that methyl group are cis, and it's perfectly okay for me to say this methyl group and this methyl group are cis as well, because they're both below the plane of the ring. So it's perfectly okay for me to make relationships between two things, but once I try and name something, it's got to be unambiguous. So that third group cannot be cis or trans. It cannot have a name of cis or trans. On the other hand, without it, then this is the other conformation of cis 1-T-butyl 3-methyl cyclohexane. So there are two different conformations here. One of the problem that I will most likely ask you is to say, write all four, label the cyclohexane chairs as cis or trans, and then rank all four. So we just did half of that problem by doing the two cis's. But since we did the two cis's, the next step would be which one's more stable than the other. So which one's more stable, A or B? Do we have an answer? Okay. 1, 2. Okay. Now, I didn't hear everybody say something, but hopefully in your head you were saying B. So B is more stable than A. That was going to be my next question, was why. Okay. Well, what's the rule? The rule for cyclohexanes is...
Isn't it like the larger groups in equatorial position are most stable?
Right. So in this case, having both of them equatorial is going to be the most stable. So the groups prefer to be equatorial versus axial. Why is that? Well, because if I look at A, the issue with A here is that the methyl group and the T-butyl group are undergoing 1,3 diaxial interactions. And so these groups are really close in space. Everything that's on the same side in an axial position is competing for a limited amount of space. And it's already interacting with the hydrogen, and this T-butyl group is already interacting with the hydrogen as well. So that's bad. But then in this case, the methyl group and the T-butyl group are going to basically clash against each other. That's what they call the steric hindrance, or steric strain. Because what we have are atoms which are clouds of negative charge, and they're going to repel each other. Now in this case, you would have steric interactions, and if I was to actually model this, that methyl group and T-butyl group, they would actually bend away from each other, which would then be not specifically a torsional strain, but similar to it. They would physically bend the ring. They would bend those bonds out of being perfectly axial because of the size of the atoms.
Could we draw the Newman projections for each of them?
We could try. We can try and draw the Newman projections looking down the carbon-carbon bond. So if we do that, then let me do this. Let me copy this slide and paste it here so that I can not erase, because when I copy and paste it doesn't let me erase. So we'll go back to this one and we'll erase this. Okay. So if we were going to look at the Newman projection of a cyclohexane ring, what we have to do is, I'm going to get rid of these as well. So we're down to what we were at the basics. Okay, we're going to look down these two carbon-carbon bonds in the ring. So the ring is made up of 4 carbons that are in the same plane, and then the one below and the carbon above that makes the ring. So these 4 bonds are in the plane. This one is raised up, that one's raised down. That's how we get the chair. So whenever we're doing a Newman projection on a cyclohexane ring, we're going to look at those. We're going to look down those 2 carbon-carbon bonds. So I'm going to come over here, and I'm going to look down those 2 carbon-carbon bonds. Now, when I do that, this position and this position, these 2 positions are going to be axial straight up. Okay? And whenever you have an axial, I'm gonna also label this, what did I label this? Number 3. I'm gonna go ahead and call this 4, and I'm gonna call that 5. So carbon 5 is gonna be on the left, and so it's gonna look like this. And carbon 3 is going to be over here, and it's going to look like that as well. Okay, so if I'm just looking down the 5-6 bond and the 3-2 bond, I'm going to see these 2 Newman projections. And these positions right here, those positions right there are the axial up positions. So there's a hydrogen here, and then the methyl group is there. So that's what carbons 3 and 5 look like. Then off to the right on carbon 3 is the H, and then off to the left on carbon 5 is also an H. What's in between those 2 carbons? What's in between carbon 3 and carbon 5 is carbon 4, which is the CH2 group. So the CH2 group is what's attached to both of carbon 3 and 5, and so that's carbon 4. So this side is carbon 3, this is 5, and then 4 is the CH2 in the middle. And it's down. So that's this. That CH2 right there is that CH2. Everybody with me so far? So then what about the back carbon? Well, a chair cyclohexane is set up so that all of the Newman projections are going to be staggered. So the back carbon then is the big circle. This is carbon 6, and this is carbon 2. And so they have positions that are what? They have positions that are axial down. And then then carbon 3 has a position this way, which is the equatorial that way, and carbon 6 has an equatorial position that's out there like that. And then we have these two positions, and now what's attached to those two positions? Carbon 1. So this CH2 is now carbon 1, and it's attached to the back carbon, carbon 6 and carbon 2. And what does carbon, that's not a CH2. That's the carbon with the terse butyl group. So if we wanted to represent that chair as a Newman projection, that's how we would do it. And so that's how it would look.
So the other two lines just be hydrogens?
Yes. So the rest, all the rest of these are simply hydrogens. Because the only thing that's not a hydrogen is this methyl group and that T-butyl group.
We really need to be able to take a chair to a Newman projection, or is it not?
Well, I did it now, so it could be fair game, but is it something, number one, is it something I want to grade? If you're all artistes to be able to draw it that way, but that, I mean, that's a tough one, and this is a tough one to draw, and I did do this in Piazza. I did do one of these, and I tried to color code it as much as I could to try and get. But what you really need to do is to sort of look at this, try and look at this in a model and see if it looks any better. And that's what I'm going to try and do here. Is try and see if I can show you that a little bit better here, just to complete the answer. So cyclohexane, no. So here's my chair. So I'm over here looking at it this way. So here's what I'm going to do. Let's see if this works. I'm going to rotate it around so that it looks like this. That. So here's your front CH2. Here are the two carbons we're looking down the Newman projections of. The one on the left that has the axial up, axial front carbon, axial up, equatorial, equatorial, axial down, axial up, front carbon, axial to the right, axial down, equatorial on the back. And then here's my CH2 on the back. So this is what I'm looking at. And I can make it look a little bit more like the Newman projection if I put the balls and the sticks in. if I put a terse butyl group on this and a methyl, here's one of the, here's the conformation where the methyl group is over here, the T-butyl group is there, so the T-butyl group is in an equatorial position, and the methyl group is in an equatorial position. And so if I make a space filling model of it, yeah, it looks congested, but it's not as bad as the T-butyl group being in an axial position up. Now the question is, this is probably not in the database. It is in the database, good. But this is the cis terse butyl that's in the database, so now let's see if I can do this one, that one. That one. And so in this case, the next highest energy keeps the T-butyl group in the equatorial position over here and puts the methyl group in the axial position. And, well, actually, what it did was, if you look at this, it's not a chair anymore, it's like in a boat. The steric interaction between this terse butyl and this methyl is so bad that it twisted that ring out of the chair. And it went up 32 kilojoules per mole, which is 7-something kilocalories. So, and this is what it would actually really look like. So if you tried to put the T-butyl and the methyl group both axial, it would deform the ring. There's so much steric interaction. So that's what it would look like. It's easier on paper, because then we don't get into the reality of deforming the ring. So. There. So that's what it would look like.
Would the trans have the same one axial position?
Well, we can finish those out and do the transes. How am I going to do that? Okay, so here's my A and my B are both cis, right? These are both cis. I need to go back to a regular pen. So those are both cis. Now, well, it does let me erase. So let's do the transes. So the trans would be, let's draw two more chairs, and now let's put the trans in place. So again, T-butyl group axial, and then T-butyl group equatorial. Again, carbon 1, carbon 2, carbon 3. So if I want my two trans conformations, then what should I do? Where should the methyl group go here on 3? If the T-butyl's axial, where does the methyl group go here? It goes into the, just shout it out. It's going to go into the equatorial position. So I'm going to have my hydrogen here, and I'm going to have my CH3 position there. Okay. And then over here, where should the methyl group go? Axial. Okay. So again, T-butyl group above, methyl group below, trans. T-butyl group below the plane of the ring, methyl group above, trans. So those two are my trans conformations. Still with me? So call those C and D. So we want to rank these from most to least stable. So which one's going to be the most stable? And your choices are A, B, C, or D. B is going to be the most stable. Do we all agree with that? Well, in that case, both alkyl groups are equatorial, which is the most stable for anything. So B will be the number one most stable. What's the least stable? A is going to be the least stable because in that case both of the groups are axial. So this one's number 4. Okay. So for a 1-3 substitution pattern, the number 1 and number 4 will always come from the cis. Which one is number 2 of C and D? Which one is more stable? Do we all agree it's D? So again, it's about size of group. If I got to have a group axial, which I do in this substitution pattern to make trans, one group's got to be axial. In this case, it's going to be the smaller group, which is methyl, which makes this number 2. And then when the T-butyl group is axial, it is number 3. So this is more of a problem that you'll see on the older exams where I give you the name and say write the four chair conformations, label them cis-trans, rank them in energy from number 1 to number 4. Most to least stable. What else?
Can we do another example of what we did last time with the Newman projections and drawing 6?
Okay, let's see. Newman projections. Let's do let's do 2,3 dimethyl pentane looking down the C3 C4 bond. So looking down the C3 C4 bond, what would be the 3 staggered, 3 eclipsed conformations of 2,3 dimethyl pentane and ranking them from number 1 to number 6 most to least stable. And I will do this for you. I will write out the blank 3 staggereds, and I will write out the blank 3 eclipsed. Now, you write the first one. So you write the first Newman projection, because if you don't get that right, you ain't gonna get the rest of them right. So write the first one, and after you write it, maybe check it with the person next to you and see if you're either both right or both wrong. no. No, there's many different ways that this could be drawn, but I'll show you. I'll show you what's correct, and it doesn't matter what you start with. You're going to end up with all 6 of them, regardless of what you start with. But you got to get the first one right.
When you say we have to start right, you mean we have to know what's attached to the carbons?
So you got to get the groups that are attached to the front carbon correct, and the groups that are attached to the back carbon correct. If you get that correct, and then then it's just a question of rotation. Okay. Does everybody have something for number 1? Or have no idea where to start? I mean, I don't expect anybody to be going, yeah, I have no idea where to start. But I have no idea how to start. I have no idea how to start. Tell me. Somebody help me. What should I do?
I would not with like the CH3, CH2, so I could kind of like get a better visualization of what each
Okay.
one is.
Okay, so you decided 3 is the front carbon and 4 is the back carbon. Okay.
And then the 3 things that are attached to 3, so you have
Okay, what are the 3 things attached to carbon 3?
you have your CH3, your methyl, and you have your CH with the 2 CH3s on it.
Which is called an and then you have what over here? What's that CH3 CH3 group called? That's an isopropyl group. So are those the 3 groups that are attached to the front carbon? Carbon 3? Yes. Does it matter where I put the methyl and the isopropyl and the hydrogen? No. When I'm grading this problem, the first thing I do is I look and I make sure that you have a carbon with a CH3 isopropyl hydrogen. Then I look at the back carbon and see what you got attached to that. So what's attached to carbon 4?
Why is it hydrogen attached to
CH2. Because the CH2, so the 3-4 bond is what's being drawn when I draw the Newman projection. So the front carbon is 3 and the back carbon is 4. So the 4 carbon is what I'm going to add my groups to in the back. So the 3-4 bond, what I should have said is, what's attached to carbon 3? Well, carbon 4. But that's already in the Newman. So now the other 3 groups are attached to carbon 3. So what's attached to carbon 4? Carbon 3, but that's already built into the Newman. So what else is attached to carbon 4? A CH3 and 2 H's. No, because if you don't write H's, remember our definition, the end of the line, an end of a line is what? It's a CH3 group. So if you want an H there, you got to put an H there.
I feel like isopropyl is just like a line of like CH3, CH3.
That would be fine. So that's what I'm going to do is I'm going to look at the front, I'm going to look at the back. Now if you have the back as the front and vice versa, I can handle that. If you just leave 2 hydrogens off, remember, that means I have to go, I wonder if they just left the hydrogens off. So I have to take a guess as to whether you intended to leave the hydrogens off or not. What is the rule? I always guess wrong. So that means they wanted 2 methyl groups there. So don't make me guess. So once we have that set up, then it's just simply a question of saying, okay, let's hold the front carbon and rotate the back. This one. That came from this hydrogen right here. So if I could have done this. I could have said C with an H. So it had an H, sorry, wrong one. C with the H. That's the H. So attached to carbon 3, there's a methyl group, an isopropyl group, and the hydrogen. So this is the critical part of this problem, because if you don't get the structure right, you're making your own problem. And then I would go through and I would just say, okay, let's go ahead and I'm going to take the shortcut by writing the isopropyl group that way, by writing it like that, and then I'm going to keep the front carbon in exactly the same position through all 6. And now for the back carbon, I'm going to rotate. I'm going to start rotating the groups. So if I start rotating the groups, my methyl group is going to come down here with my 2 H's. Then my methyl group is going to rotate to the upper left with my 2 H's there. And so there's 1, 2, and 3. Sorry, A, B, and C. And then down here, I'm going to basically either rotate clockwise 60 degrees or back 60 degrees. If I rotate clockwise 60 degrees, that's going to put the methyl group and the isopropyl next to each other. Then I'm going to rotate the methyl group to the left. And then I'm going to rotate the methyl group to the top. And so there's my other 3. So now I've got A and B and C and D and E and F. Ranking them in terms of energy. Which one's going to be the most stable of A, B, or C? Do we have an answer? Okay, A, B, C. That finger is the 1. A, B, C. Okay? So on 3, give me which one's the most stable? A, B, or C? 1, 2. I heard C's. So C's. So I hear C. Do we agree with C? I agree with C. Why? First thing, number of Gauss interactions. 1, 2 Gauss interactions versus 1 Gauss interaction versus 1 Gauss interaction. So B and C each have 1 Gauss interaction between the non-hydrogen groups, and A has 2. So A is automatically the least stable. This is number 3. Methyl isopropyl versus methyl Gauss. What's worse? The bigger the group, the more destabilizing the interaction. So 2 small methyl groups is better than methyl in some bigger group. So this one then becomes number 1. This one becomes number 2. And then for D, E, and F, D has 1 eclipsing interaction, E has no eclipsing interactions, and F has 1 eclipsing interactions. So E, all the hydrogens and isopropyl groups are eclipsing hydrogen, but that's all they got to eclipse something, so hydrogens are the best. Then methyl eclipsing versus methyl isopropyl, which one's better, which one's more stable? Methyl. All 3 staggereds are always more stable than all 3 eclipse. The worst staggered is always better than the more stable than the worst, or than the best eclipse. Okay? So if you have any questions, if you look on Canvas, I posted this morning's notes and questions they asked, which are somewhat similar to what we just did. But if you want a second explanation, you can go to that. Put any questions on Piazza, send them to me privately or whatever. I'll post them on Piazza. I will guarantee you I will at least be in like noonish to like 6-ish on Sunday afternoon. I'm not quite sure. I will be in before 2 tomorrow, but I'm videotaping something. And then I'm not sure if I'll be in the afternoon, but I will be on the computer. So if you have any questions, certainly email me. So if you have any questions, email me. Otherwise, there's older exams online you can take a look at. But if you have any questions, put them up there. I will answer them, okay? And let's see. Katie